Hello everyone. In this lecture, we're going to switch gears a little bit and discuss vector equation. So basically, a matrix with only one column is called as a vector in Rn. So we read this as Rn, and that means the n-dimensional Euclidean space. So there are two examples about vectors. The first one has two entries, which means it belongs to two-dimensional space. And the other one has four entries, so it sits inside the four-dimensional Euclidean space. So to distinguish vectors and scalar, we use this arrow notation above. And the textbook uses both ways to distinguish scalars and vectors. Okay, so suppose that you have vector given by 3 and 8, then 3u is a scalar multiplication of u by 3, which means we just scale all the entries by 3. That gives you 9 and 24. And negative u then equals to negative 3 and 8. Also, if the vector w is given by 5 and 0, then we can add u and v. Oops, this one has to be w. So we can add vectors component wisely. So u plus w gives you 3 plus 5 is 8, and negative 8 plus 0 is negative 8. So note that we can only add vectors of the same size. So for example, this is actually a non-example. We cannot add, say, like 3, 8 and 1, 0, 4 vector. So this one certainly doesn't make any sense because this is 2 by 1 matrix and this is 3 by 1 matrix. So geometrically, we can associate a vector in Rn with a point. If u and w's are given in this way, then u corresponds to a point 3, negative 4 in R2, and negative 1, 2 corresponds to a point negative 1, 2 that sits inside R2. So basically, or the symbol means an element of, or you can just read that as the word in. So to distinguish vector with a point, we draw an arrow starts at 0 and ending at the point they're associated with. So this arrow corresponds to the vector 3, negative 4, and this arrow corresponds to the vector 1, 2, negative 1, 2. Okay, so geometrically, we can add vectors by using parallelogram. So suppose that you have a vector u given by 4, 1 and w given by 1, 2. Then you can add the vector by drawing a parallelogram, and this one corresponds to u plus v, u plus w. Then to get to this point, when you start from the endpoint of the vector u, from 4, 1, you have to go over by 1, and you have to go up by 2. That gives you 5, 3. And the scalar multiplication is simply the scaling of the given vector. So suppose that you have the vector given by 1, 2, then w is over here, the arrow from origin that ends at 1, 2. Then 2w corresponds to 2 times bigger vector than the given vector w. So 2w corresponds to this, and the end point of this one should be 2, 4. So we can write 2w as 2, 4. Okay, so similar to what we have in the real numbers, there are several algebraic properties of vectors. So first of all, vector addition is commutative, which means if you have u plus v, then this is the same as v plus u. So you can add vectors whatever order you want. And also, if you have u plus v and plus w, then you can unpair this parenthesis and pair this again with v plus w. So vector addition has associativity. And there is zero vector, which is called as identity, that doesn't change the given vector if you add 0 to them. And there is the additive inverse that makes your vector equals to 0, which is negative u. So suppose that you have c and d as a number, then we can certainly distribute scalars into vectors, which means c times u plus v is the same as cu plus cv. And also, if you have c plus d times u, then you can distribute vector into the scalar. And if you have c d times u, this is the same as c times du, which is associativity of scalar multiplication. And finally, we have identity for the scalar multiplication. So suppose that you have p number of vectors with p number of scalars, that the linear combination is the combination of your vectors with scalar multiplication. So this whole vector is called as the linear combination of your given vectors v1 through vp with weight c1 through cp. So for example, if you have two vectors v1 and v2, then 5 times v1 plus 2 times v2 is a linear combination of v1 and v2. And 0 is also a linear combination, even though there is no v1 and v2, because we can simply choose c1 equals to 0 and c2 equals to 0. And this gives you 0 in terms of v1 and v2. Okay, so let's look at this exercise. So we need to verify that the given vector b is a linear combination of v1 and v2. And actually, there's a typo. So the second row of v2 should be positive 5 instead of negative 5. So this asks us to find out, are there any scalars x1 and x2 such that x1 times v1 plus x2 times v2 equals to v. So here, people frequently abbreviate such that as s comma t. Whenever I write as t, this means such that. So if you write the equation in a matrix form, we certainly have x1 times 1, negative 3, 4 plus x2, 0, 5, 6 equals to 3, negative 19, 0. Or in other words, we have x1, negative 3x1 plus 5x2, 4x1 plus 6x2 equals to 3, negative 19, and 0. So this gives you x1 equals to 3, negative 3x1 plus 5x2 equals to negative 19, and 4x1 plus 6x2 equals to 0. This gives you a system of equation. So if you plug in the first one to the second one, then this gives you negative 3 times 3 plus 5x2 equals to negative 19, or 5x2 equals to negative 19 plus 9, that gives you negative 10, so we get x2 equals to negative 2. So we have to plug in the solutions into the third equation to check whether the system indeed has a solution. So 4 times 3 plus 6 times negative 2 is actually 0, so there's no problem. So the given vector b is a linear combination of v1 and v2, and you can write b as 3v1 minus 2v2. So here, one thing that we can observe that, so if you write the system of equation as an augmented matrix, then this gives you 1, 0, 3, and negative 3, 5, and negative 19, and 4, 6, and 0. So if you compare this with the given information above, so v1 was 1, negative 3, and 4, right? So this one certainly goes to the first column, and v2 goes to the second column, and B goes to the third column. So in general, the vector equation x1 v1 plus x2 v2 dot 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 plus xn vn equals to b has the same solution as the augmented matrix given by this. Okay, so there is a geometric interpretation of the linear combination. So for given u and v, let's say A to be v minus u, the vector b as 2 times u, and c to be u plus v. So suppose that v is given by this vector, and u is given by this one. Then to get u plus v, we want to find the parallelogram using the given two vectors. But if you extend this parallelogram, like something like this, so here A corresponds to v minus u, which means you go opposite direction of u. So this vector corresponds to v minus u, and 2u corresponds to this vector. So basically, it's really like a new gradient system. So here we call this system as the span of the given vectors. So suppose that you get a vector from Euclidean space, then the set of all linear combination of the given vectors is called as the span of the given vector, and we write the span as this way. So let's look at examples about the span of the given vector. So suppose that you have only one vector, a single vector from R3, then the linear combination of v is just a scalar multiplications of the given vector v. So if you have the vector given in this way, then the span of v corresponds to this line. So the span of v is a line through the origin. And now let's suppose that you took two different vectors, v and w, from R3. So let's say your vector v to be this one, and w to be that one. Then the span of v and w corresponds to a plane through the origin containing vectors v and w. So intuitively, one can think that span is just taking off the gradient system of the given vectors.